In order for the process of action potential to begin, the axon terminal must first come near the muscle fiber. The terminal, however, does not come into direct contact with the fiber, thus leaving a gap, which is called the synaptic cleft. In the axon terminal, calcium triggers the release of acetylcholine, or ACH, represented here in red. The ACH then attaches to ACH receptors, which open up sodium-potassium pumps, shown in purple. Now, outside of the muscle fiber is positively charged due to a high concentration of sodium. On the other hand, the inside of the muscle fiber is negatively charged due to the high concentration of negative proteins in DNA. Once the sodium-potassium pump is opened by the ACH receptors, sodium enters the muscle fiber. This increase of sodium causes the inside of the cell to become positively charged. This is called depolarization. Since the inside of the cell is now positive and the outside is negative, the cell wants to return to a balanced charge. In order to do this, potassium exits the inside of the cell, which causes the inside to return to a negative charge and the outside to a positive charge. This is called repolarization. The process of sodium entering and potassium exiting the cell is simultaneous, since the negative and positive charges are constantly being attracted to one another. This slide shows the transfer of positive and negative charges between the inside and outside of the muscle fiber. This slide shows the phases of action potential. In step 1, the resting stage, both the sodium and potassium pumps are closed. Resting stage always begins at negative 70 millivolts. Step 2, depolarization, is when sodium enters the muscle fiber from the synaptic cleft and the sodium gate opens. In step 3, repolarization, the potassium gates open and action potential is reached. In step 4, hyperpolarization, both of the potassium and sodium gates open. After hyperpolarization, the millivolts begin to increase and the phases of action potential begin again.